We are now back to calorimetry and tracking. So Joy is going to give the second lecture today.
Okay. So the first thing that I want to say is yesterday in the discussion session, someone asked me, I can't remember who, someone asked me what the volume of data that collider facilities are actually producing, or at least I think the discussion was in association to Rick. And so I found a talk and looked this up. So the entire Rick facility generated 1 petabyte of data in 2001. In 2017, we had collected 100 petabytes of total data. And as of yesterday, there are about 300 petabytes. So we've collected like 200 petabytes in the last, 7 years or something like that, of which SPhoenix is responsible for 20 of those petabytes. So I can't remember who was asking about this, but that's an indication of the size of the volume and also how it's really grown over the last 2 decades, at least in the case of Rick. I'm sure, I know for certain that the LHC is even, I think in this figure, the LHC is, the high luminosity LHC is expected to generate 100 or 800 petabytes per year. So that will be in several years, but these are massive amounts of data volume. Okay. So that was a complete side remark, not related to what will be discussed today. Well, I guess it is related, but so this is calorimetry and tracking day 2. Uh-oh. Can't move. Oh, okay, awesome. Okay, so just as a quick review from what we talked about yesterday. So tracking, we have a small material detectors that are towards the very center of the barrel here that measure signals where particles traverse. We use these signals to determine the particle trajectory that is in a magnetic field, to measure the free momentum, the charge, and the position of origin of the track. And then we have, outside of this, the calorimeters, which are dense material detectors to stop particles. And then we use these signals to determine the particle energy. And these are for measurement of charge and neutral energy. So we can measure things like photons, electrons, neutrons, and charged hadrons. Okay, so I ended the lecture yesterday asking, now what do we do with this? So all that we have discussed so far is that detectors register some pulse or signal, which is typically called a hit. And this does not tell us anything about the particle itself. You have a single detector layer that has some pulse in it, and that does not give you a free momentum or a charge or anything like this. So what is necessary is that we have to reconstruct the data. So we have to take these hits like puzzle pieces and figure out how to put them all together to make a real physics event that we can do some data analysis with to then make some measurements like many of the measurements that Yi showed this morning. So event reconstruction is basically the general process of putting all of these pieces together, starting from something like a pulse or a signal or whatever it is, a waveform in your detector, taking that, combining it with other subsystems, maybe for additional information, and then slowly building more and more physics-like objects, or the things that we think about when we talk about an experimental measurement. So basically, the idea is, in this JF4 simulation, this is a simulation of a bottom quark jet, a V quark jet. And the question is, how the heck do you go from this to an actual physics measurement, which is something like an RAA that we can learn something about the medium properties in the quark gluon plasma with these V quark jets. So somewhere in the middle, there's a lot of work that goes on to actually be able to do this. And that's something that I really want to emphasize, because when I was a student, I had no real concept or understanding how much goes into these question marks. So I hope to convey to you that there is a tremendous amount of work that has to be done to actually fill in this middle piece. Okay, so let's talk a little bit about clustering. So we have sort of implicitly assumed in the discussion yesterday that one particle deposits some charge into one readout unit of your detector. And that's generally not the case because showers, as we learned, are complex. They develop, they can be extremely deep for hadronic calorimeters. They could be very wide depending on the type of shower. Particles may enter the active detector volume at an angle. Shower may develop broadly. Something that I think is really highlights this is that in this single electron J-on simulation that I showed yesterday, if you look closely, this electron enters almost exactly normally to the block, to the calorimeter tower, and almost in the middle of the tower. And even still, it's producing photons and electrons and whatnot that span several towers. So this is the most idealized simulation situation, could not be more perfect. And still, you develop, your shower develops over many different towers. And this angle doesn't even show the sort of into the board depth of your calorimeter. You may have the exact same thing that is if you could see in sort of this direction. You may have the exact same thing with the shower developing longitude. So this is a super complicated process, but it's a very important one. This is an example event display from a simulation of again, bomb cork jet embedded into a heavy ion background. And this shows you all of the calorimeter towers and all the orange lines in the center are the actual tracks. And again, the whole purpose of event reconstruction is you have to build this into something that you can do some physics analysis with. So if I were to ask you right now, which one of these towers actually belongs to a photon or an electron or a hadron, you would have no idea how to actually distinguish that because this is an extremely complicated event. So the idea of clustering algorithms is that we have to take these tower energy deposits and actually cluster them together to try to say with some confidence that this cluster actually belonged to a particle. And, maybe that's an electron, maybe it's a photon, maybe it's a whatever. But clustering, the job of clustering is to identify which of these towers belong to the same particle, which of these calorimeter towers. So there are lots of different clustering algorithms that have been developed, much like the actual calorimeters themselves yesterday, like we talked about. They all have pros and cons for different use cases, depending on what your sort of environment is. So the simplest example that you might think of is shown here in this little cartoon. So suppose you have a 3x3 tower block of the calorimeter. So this is some like sampling calorimeter or something like this. And each one of these towers registers some ADC that we'll just call a number for the purposes of the cartoon example. The simplest clustering algorithm that you could possibly consider is which tower had the highest ADC or the highest number, which one had the most charge deposited into it. And that would give you this red dot. So you might say, okay, the exact center of this tower is where my particle was. In reality, that's probably not going to give you very good position or energy resolution. So maybe you do something more fancy and you say, I'm going to look at the highest energy tower and then also the 8 surrounding towers in a 3x3 sum. And I'm going to take some energy weighted sum of these towers. And that will give me this blue dot maybe. That will tell me, okay, the position of the cluster was actually here. And it has some energy weight that we determined from these actual numbers. So you could imagine that this would change your position and energy resolution dramatically just by doing something sort of the leading order step of going from the single maximum energy tower to an energy weighted 3x3 sum. So A much more complex example is something like island clustering or topological clustering that is used in many different experiments. This is an example dijet event display from some Atlas simulation from quite a while ago now, where they show things in terms of these sort of characteristic angles in their algorithm. But what I want to highlight is that if you look, it's probably tough to see on this slide, but if you look on the slides yourself on your computer, you'll see that there are black lines kind of drawn around the various clusters. And if you were to look at this by eye, you would probably say, again, if there were no black lines at all around these sort of thick black lines around these clusters, it would be very difficult by eye to sort of say, this tower belongs to this cluster, this tower belongs to this cluster. But this clustering algorithm is able to identify this. And for example, with this particular algorithm, Atlas has decided, through their various tests and whatnot, that this very accurately or adequately for their physics program actually determines things like cluster energies and shapes for doing their physics. So in the case of something like island clustering, you can think of an example, or you can think of a more complex example where you take some maximum energy tower and you look for local maxima and minima in the energy distribution, and that's how you define your clusters. And you define some algorithm that identifies these local maxima and minima and shares the towers appropriately. So there are all sorts of things that you can do, but the point of this is to just emphasize that it's really important because you can greatly improve your position and energy resolution for the same sort of calorimeter. Okay, so what should a really good clustering algorithm do? It should determine the best position and energy resolution possible, limited only by the inherent detector resolution. It should properly assign neighboring towers or energy deposits to the appropriate cluster. And this can be very complicated because not all clusters are equal, and not all showers are equal. They develop in different ways. If you have particles that traverse your material at an angle, that will look very different than a particle that is sort of normal to the calorimeter tower. So you want to try to get the cluster shape correct for all of these different scenarios. You want your algorithm to mitigate effects from detector noise, beam pileup, whatever other backgrounds you have. So you don't want to sort of artificially include energy deposits that maybe shouldn't be. And you can even think of something that's super complex, which is what the topological clustering algorithm is, which actually connects clusters from adjacent calorimeters. So you could build a sort of super cluster that connects energy deposits in the EM-cal with energy deposits from the H-cal, if you are convinced enough that they are really belonging to the same particle. And that's going to depend on your detector geometry, it will depend on your all sorts of things like this. So this is a kind of cool picture from this Atlas paper that I think is very instructive for you to sort of see the level of detail that goes into some of these algorithms. So this sort of blob here is a example shower. And in this particular clustering algorithm that Atlas develops, these are all of the different parameters and sort of things that they try to identify with the cluster. And there's a whole list of things here. There's the center of gravity measured from the nominal vertex. There's the geometrical center of an actual calorimeter tower. And then you can define angles and vectors with respect to the various shower properties and calorimeter towers. And all of these things can be used to try to identify and understand how the shower should actually look based on some particular input particle. So these kinds of algorithms can become very complicated very quickly, but the more complicated they are, the more information they give you about your particle and its development in the calorimeter. Okay, you can also use information from your clustering to help with particle identification. So we saw yesterday that sometimes you can have a pion, for example, start showering in the EM-cal. because there's material there. So in principle, there's no reason why it might not ionize or interact with some part of the material. Maybe a pi zero is created, it decays to 2 photons, and you start some shower in the EMCal. The development of the pion versus the electron shower is very different in the EMCal, which is exactly what you expect. That's why you build it that way, so that the EMCal actually detects electromagnetic particles. So this is an example. This plot on the right here shows some simulation for some pions and some electrons as a function of this chi-squared value, which is some shower shape type of variable that was defined in this paper. And you can see that electrons and pions look very differently. What this is basically saying is that the shower shape is consistent with that of an electron versus the shower shape being consistent with more of a hadron, which is going to be broader and more deep like we discussed yesterday. And so you can use this kind of information to, given your cluster, say, I'm much more confident that this is an electron rather than a pion. If you were to make some cut here at very low values of this chi-square. You can see this also in this plot here, that this may depend on the energy of the cluster. So this shows the hadron rejection, which is effectively how many pions you can reject from your EMCal based on their shower development. And you can see that this gets much better at higher momentum because the hadron shower becomes deeper. So it's easier to actually identify if it's going to look like an electron shower or look like a hadron shower. Okay, so calorimeters are not perfect. We discussed that yesterday. There were some questions yesterday about, what if energy gets out of your calorimeter? How do you know that if energy is leaking out the sides? So that definitely happens. Energy can escape detection or might be completely lost to mechanical constraints. This plot here is an example of this. So what this is basically looking at the face of the calorimeter. You're looking at the sort of Y versus X position of the calorimeter. And if you shoot 8 GeV electrons into that calorimeter, the Z axis, the color axis here, shows you what energy you reconstruct from those 8 GeV electrons. And you can see there's a huge position dependence. You're much more likely to, if you look really carefully at this, if you stare carefully, you'll actually see that there's a symmetric pattern of 2 by 2 blocks where there are red sort of maxima in these block shaped structures. And that's because this is where the actual calorimeter towers are. So this electron is going through the center of the tower, and the shower develops much more uniformly and is easier to read out, versus if an electron traverses at the boundary of the tower, you lose a significant amount of energy, up to 1.5 or 2 GeV, which is something like 30% of the input energy. So this is just one example that you can actually correct for these things, because there's a significant position dependence that you need to understand. You can do some correction and calibrate this out based on its position dependence. So again, this is basically a projection of the previous plot. You can think of the x-axis as just a horizontal position and the y-axis as the reconstructed cluster energy. So what you see in this left before the correction is that there's a large variability on the actual energy that you reconstruct based on where the cluster exists in the calorimeter. You can do some corrections for 12 GeV electrons and make this much flatter, such that you improve your energy resolution of your calorimeter to account for these kinds of position dependences. So again, this may, and it does, depend on what kind of input particle you have. Electrons bend in the magnetic field, and it depends on if your calorimeter is in the magnetic field or in the presence of a field. But electrons bend and photons do not. So electrons be potentially bending through your calorimeter, which will again change the way that the shower actually develops through your calorimeter, versus a photon, which will just go straight through since it does not, since it's not charged. Okay, so let's talk about track reconstruction a little bit. Clustering is also used. Oh yeah, go for it.
So in calorimeters, the whole point of clustering just to like group a shower together, so you know if their shower is like one.
Effectively, yes. So you, again, if you remember from yesterday, your number of radiation lengths determines how much of the incident particles energy will deposit into the calorimeter, right? But it does not say where that energy will be in your calorimeter. So the job of the clustering algorithm is to try to group that energy together so that you really can properly or to the best ability that you were able to assign the correct energy to the incident particle. Okay, any other questions about that before we move on? You tracking? Okay. So you can also do clustering and tracking, and it's also extremely very useful. Oftentimes for tracking detectors, clustering is performed in local coordinates. So I think this is a very good distinction to point out that many detectors, and this is true for calorimeters as well, many detectors operate in local coordinates because it is an easier system to use in the sort of defined geometry of the sensor or the tower or whatever. And you can actually move these local coordinates to global coordinates just by performing an affine transformation, which is sort of shown pictorially over here. So in the local coordinate system, you have the x-axis maybe along the sensor, the z-axis in the other direction, and then the y-axis out of the board. And then you can perform your clustering in only 2 dimensions, which generally simplifies things. And then just perform an affine transformation to move this from, for example, the global origin to its actual position in your detector. So again, clustering is extremely important for tracking detectors because in general, your particle does not just leave some signal in one single chip or pixel or whatever of your detector. So generally your clusters have some shape that may not be a priori known. And if you want to get the best position resolution out of your tracking system, you need to properly identify the cluster shape so that you can minimize the cluster position resolution, and that will then have a direct effect on your momentum resolution as we discussed yesterday. And again, this may be highly dependent on if the track is traversing the sensor at an angle or normally to the surface. You can imagine that some particle that's going straight through this cartoon here may leave charge in fewer pixels than one that is traversing at an angle, which may leave charge in more pixels. So just to sort of highlight and emphasize that this is important, this is a plot that shows the average cluster size in the silicon pixel detector of S-Phoenix as a function of the pseudo rapidity. So basically how far out you are at Z effectively in this particular plot. And you can see that the cluster size is always more than 1. And it averages something like 3, but can be as high as 8. So that means for a single cluster, there are 8 pixels that are attached to that cluster. And so again, you can imagine that your position resolution, if you were to take some very simple algorithm of just what is my maximum energy pixel, that's going to give you significantly worse position resolution than some more complicated algorithm that groups things together and finds something like an energy weighted average. And then that has direct consequences to your tracking momentum resolution. Okay, so let's talk a little bit about, now that we have clusters in our tracking detectors, let's talk a little bit about track reconstruction. So track reconstruction requires correlating clusters across detectors. So remember, we only actually measure things that are on our plane, on our readout planes, wherever those are. So for a single track, I think it's pretty easy to see how you could do this. You could sort of easily pick out the clusters along in this cartoon, the clusters along the track. and it's probably straightforward enough to write an algorithm that does this. Okay, so now what about if you have 20 particles, or what if you have 10,000 particles that leave hundreds of thousands of clusters in your tracking layers? What if your detector has hot or dead areas where the track maybe should have left a cluster but didn't? You have some hole in your detector effectively. What if many of the clusters are from background sources not associated with your physics event? Again, in this sort of simple cartoon, now if I were to ask you, where is the track in this picture? It would be very hard for you or an algorithm to actually identify this because there are so many combinatoric possibilities. So there it is, but it's hard to see that, especially when you may have more than one particle, you may have many particles. You don't a priori know that. So track reconstruction is an extremely challenging task for modern nuclear and high energy physics experiments because of the extremely high luminosities that are being delivered to the experiments. So that's of course a great thing because we get more data, so we can do more statistically hungry measurements, which are usually the ones that we're interested in. But it makes our event reconstruction challenge much bigger. So there are three sort of stages of track reconstruction. There's track seeding, which is obtaining an initial guess for the track. So that's shown in this little cartoon here as these three dots. So your seeding algorithm, the goal of your seeding algorithm is to find to be as efficient and pure as possible at finding a track, a set of clusters that really belongs to a real particle rather than some combinatoric association or some background or whatever. Track finding is then the next step of the track seeding process, which is adding additional clusters to the track. So once you have your seed, which maybe does not consist of the entire track, your track finding algorithm's job is to try to connect other clusters that belong to that track so that you again maximize the lever arm and the number of measurements on your track to get the most precise momentum resolution. And then track fitting is the final step, which is to determine the final track parameters precisely. So what are the track parameters? These are what we usually think of as the momentum and the origin or position of closest approach of the track. Any track reconstruction algorithms nowadays, like ACTS, use this parameterization here, which actually reduces the number of parameters and makes the computational speed of many of the calculations faster, because instead of 6 parameters of PX, PY, PZ, 3 momentum, and a 3 position, you can actually reduce this. One of those parameters, you can show one of those parameters is redundant. And you can reduce this to a 2 position, where L0 is basically the radial distance, and L1 is the Z distance of the particle's closest approach. And then theta, phi, and theta are the usual azimuthal and polar angle coordinates. And then Q over P is the charge divided by the total momentum. So that tells you the charge of the track, and then also sort of how straight or not the trajectory is. So the goal of your track fitting algorithm is to actually determine these with some very high precision, or at least the best precision that your detector can give you. So generally, track fitting is done by something that's called a Kalman filter. You can go look on Wikipedia. Kalman filters are an incredibly powerful algorithm that use measurements as a function of time to produce estimates of unknown variables. So when you think about it, that's kind of amazing that you can take some measurements as a function of time, feed them into a Kalman filter, and your Kalman filter can actually predict where the next measurement will be without knowing anything else about the sort of system other than the location and time dependence of your detector measurements. So Kalman filters, so that's for the use case for track reconstruction. Kalman filters actually have a huge range of use cases like navigation of vehicles, signal processing, robotic motion, trajectory optimization. They're used in all sorts of fields of science and engineering, and because it is such a powerful algorithm. So in our field, common filters are used to precisely determine the track parameters via something like this cartoon. So the way that the common filter works is pretend that these planes are your actual tracking detector layers, and you have some orange measurements on them that have an associated uncertainty that's shown by the size of the blob. Your common filter, given some initial guess, will make a prediction, which is shown in blue here, of where it thinks the measurement uncertainty should be. And then it does some mathematics to make a filtered, which is shown in green, a filtered measurement, which is the common filter's best estimate of where the track actually was, given the measurement and its uncertainties. And it will continuously propagate outwards through all of, or inwards, depending on where you start, through all of your measurements until it then can calculate the final track parameters with extremely high precision. And again, the common filter's inputs only are the actual measurement positions, their measurement uncertainties, and some initial guess of the track parameters, so that the common filter can make this initial step from, for example, the origin or the particle's closest of approach to this first detector layer and start using the measurements to constrain itself. You can complicate this even more by adding in the track finding step to a common filter. So a combinatorial common filter is, or CKF, actually combines track finding and track fitting. And again, combinatorial common filters are a general case of algorithm that can be used for many different applications. For our purposes, we just use them for track finding and fitting. But the CKF is nice because instead of having to do the track finding yourself, you only need to provide a input track seed measurement, input track seed estimate. So if we go back a couple of slides, the input to the CKF is only the set of track parameters that are associated to, for example, this triplet here. So you might find some triplet with some seeding algorithm. And then you might say this triplet has momentum of this and a position of this, whatever it is. And then you provide that to the CKF. And the CKF will propagate that estimate out to the detector layers and try to associate measurements with the track based on some criteria, like a chi-square criteria. And the CKF will create branches of the track of clusters that it thinks might be associated. And then it is your job as the event reconstructing physicist to tune the values of the chi-square that are allowed based on your occupancies, for example, and your detector resolutions, whatever that may be. And then you may also need some ambiguity resolution because for a single input track seed, you may get many branches from the CKF of possible tracks. So in this sort of cartoon example, there is one track that's given by this sort of yellow line. I guess, well, it's sort of yellow and green highlighted. But maybe given your implementation of the CKF, the allowed branches that could be formed are all of these other connections. This is, I think, a gross over dramatization of what this might look like, because you can see that there are many sort of kinks in some of these tracks, so you would probably reject these outright. But maybe your occupancies in general, they are high enough that you can have many branches per input track seed. So your job then is to try to reduce the number of duplicates or wrong tracks that are not actually from real particles based on your tuning of the CKF. So then once you have your actual reconstructed tracks, you can propagate those back to a common origin to determine a collision vertex. And vertex finders and fitters operate very similarly to track finding and fitting algorithms, in that they might produce a vertex seed estimate that the algorithm thinks is the best candidate for the vertex, and then perform some fitting algorithm, which takes all of the tracks and tries to optimize or properly propagate their parameters back to this location with, for example, a common filter. So it's important to also to differentiate between primary, secondary, and pile-up vertices. So your vertexing algorithm should in principle be able to do this, where primary vertices are vertices from your actual collision. Pile-up vertices are from collisions that maybe happen down beam pipe or something like this. And then secondary vertices come from long-lived decays like D0, heavy flavor mesons, for example, charm bottom work, mesons or hadrons. Okay, so what I want to emphasize about track reconstruction is that it is computationally expensive. It is generally, for all experiments, the most time-consuming part of event reconstruction. And that is simply because of the combinatorics of the problem. The more clusters you have in your detector, the more possibilities you have of tracks, and the longer it takes then to filter through all of them. This is a really nice plot that shows that the time that the track event reconstruction takes scales quadratically with effectively the number of clusters in the event. So what this shows is the computational time taken to reconstruct a single event as a function of the effectively rate of collisions in the LHC. And you can see this is really starting to sort of climb very quickly as you get to higher and higher event rates. And so track reconstruction is complicated because it needs to have extremely high efficiency and purity to sort of maximize both the physics and the CPU resources that you are using. Because in modern experiments, we don't have infinite computing resources like we used to have. As I mentioned before, we're now generating huge amounts of data, and it takes a lot of computational power to actually reconstruct that data and analyze it. And so we need to use it sort of carefully and appropriately because we don't have the generally financial resources to just buy an infinite amount of CPUs or something like this. Okay, so the EIC will have some unique and some not unique in terms of other accelerator facilities challenges to its track reconstruction problems. This is a really nice table from a colleague, Jin Huang at BNL, that shows the EIC, RIC, and the LHC towards the high luminosity LHC, and shows some of the sort of general accelerator characteristics of these three facilities so that you can compare them sort of one by one. And what I want to highlight is that the EIC, if you actually look at this peak luminosity row, the EIC actually has luminosity of comparable luminosity to the LHC or the high luminosity LHC. The challenge with the EIC is that the collision rate is actually much less because you have electrons colliding with hadrons. So you have an alpha electromagnetic term, which is much smaller than the strong coupling constant. And so despite the luminosity being high, the rate at which real physics collisions happen at the EIC is actually very small. However, there is extremely large background rates compared to this collision rate, detectable physics collision rate, because we have a variety of background sources that will produce particles in our detector. So that becomes a real challenge for track reconstruction because it's kind of like finding a needle in a haystack. You may have a single real physics collision that you are interested in and want to, do some physics analysis with that happens in something like a microsecond of data, but you might have 500 background collisions that are swarming the occupancies of your detector or dominating the occupancies of your detector, from which you have to separate out that background and actually identify your measurements that are associated to the tracks that you're really interested in from the physics process. So this is a really cool table, and I encourage you to take a look at it later when you're, on your own, and really compare and contrast the different collider facilities to see how they are different and how they're similar. Okay, so you heard a lot about how at EIC, I think you heard last week already, we're going to use streaming readout system. So that means we will not trigger on the data. We're going to read out all of the data in a continuous stream. And that will maximize our physics reach because we don't have to select a particular topology of physics events. We can just collect all of the data and leave that to later for analyzers or analysis to actually identify what event topology they are interested in for the physics process that they're interested in. So in a streaming system, the event unit is really a time frame, and the reconstruction then has to operate in a time frame, identifying the real physics events, like I was saying, excluding these background tracks and trying to find the real physics event. The collision of interest may have out-of-time pileup or hits embedded in it, and it undoubtedly will at the EIC. To sort of give you a sense for what this looks like, this is 100 microseconds of streamed PP data. And what this shows is the number of tracks produced as a function of the time they were produced. So you can see this axis goes from something like a little below 0 to a little over 100 microseconds. And so in this entire time frame, your job as the event reconstructor is to reconstruct all of these tracks and then identify where they actually came from in this collision structure, so that you can, again, try to identify these tracks came from the physics process that I'm really interested in, or maybe no, they came from some background process that I don't care about. So in general, tracking and calorimeter reconstruction is moving towards 4- and 5-dimensional reconstruction because we have way more background than we have physics collisions. And so we need as much information as we can to try to differentiate and identify background from the actual physics process. So examples of these are the HGH cal that we talked about yesterday, the CA, I don't know if this is a C-Alice or Callice calorimeter, but they both use sort of a 5-dimensional, or they're looking to use 5-dimensional reconstruction. The EPIC forward H-cal is similar in this regard, a forward H-cal insert. And then track reconstruction at sPhoenix, EPIC, and the LHC are all starting to integrate timing and position into their reconstruction out of necessity. Otherwise, we are just background dominated. So I think this is a really instructive way to see the power of time in track reconstruction. So this is some simulation, again, in sPhoenix PP collisions where we stream some data out over some time frame. And what this shows is the number of tracks as a function of the time that the tracks were produced. So the TPC in sPhoenix has a really slow readout time of 13 microseconds, while RIC collides the proton bunches at rates of 100 nanoseconds. So what that means is that if you divide those two numbers, you'll see that the TPC is sensitive to literally the entire RIC bunch structure. So the TPC at any given time has tracks in it from every single bunch crossing in the RIC accelerator. And you can see this in this plot, which shows that there are tracks. If you just look at TPC tracks, there are tracks from all sorts of times produced over the entire spectrum of this particular simulation. If you zoom into this plot, you can see that these tracks literally follow the 100 nanosecond bunch structure of RIC. So this is exactly what you would expect to see, that there are tracks in 100 nanosecond intervals that are in the TPC at any given time that you're trying to measure this. If you then take this a step further and you say, I want tracks that have TPC measurements and also some silicon measurements, you reduce this range dramatically. And now you have tracks from your sort of bunch crossing of interest, which is at time 0, but you have many, many fewer tracks from the times outside of this bunch crossing. And if you take this a step further and require clusters from a very fast silicon detector, which has a timing resolution of 100 nanoseconds, which is about the RIC bunch structure, you see that you almost completely eliminate the background. And you have, whatever this is, tens of thousands of tracks at the sort of crossing at the bunch crossing of interest, and only of order tens of tracks outside, which are maybe from your reconstruction algorithm mismatching things. So this is, I think, a great example that shows the power of doing things in as many dimensions as we can and utilizing the data, or manipulating the data in a way that utilizes all of the information that we can collect. So EPIC will do something almost exactly analogous, because, again, this is a necessity at the EIC due to the large backgrounds. At Epic, the silicon detectors are going to be slow comparatively. They have a readout time of something like several microseconds. And the MPGDs, which exist outside of the silicon, are going to be very fast. They'll have a readout time of something like tens of nanoseconds. And if you go look at the table that I showed before, the EIC bunch structure will be something like 10 nanoseconds. So ideally, if you were to do some simulation with backgrounds in our Epic framework, which hopefully Kolio will show you how to do today, could see something exactly analogous to, for example, this. If you look at tracks only in the silicon, and then as soon as you require some MPGD cluster on that track, you'd presumably see something like this, and it would be very similar. Okay, so as a quick reminder, we started out saying that we wanted to know all the particles in the event. We wanted to know their form momentum, their position of origin, their charge, and maybe their particle type. So I haven't talked anything about PID because I think other lecturers have talked about this, but we can actually use tracking and calorimetry, some tricks to do some PID information, like I mentioned before with electrons and pions. But I've talked this entire time about reconstructing clusters in the calorimeter and reconstructing tracks in the tracking detectors. These in principle come from the same particle, unless they are neutral, in which case we don't track them. So the question that we can ask now is, can we combine these things? Can we say, I have a track that points to a cluster, so I can take the track's 3 momentum, I can take the cluster's energy, and I can really try to create a 4 momentum that is a true sort of particle identification type of thing. So this is exactly the concept behind particle flow algorithms, as they're so called. They connect tracks, particle flow reconstruction algorithms connect tracks to calorimeter clusters to try to create 4 momenta of the particles and really say, go from a track or a cluster to a real particle object. So in principle, as is always the case, this is easy. For example, if we go back to our sort of dummy simulation here with an 8 GeV electron going into our calorimeter tower, you could by eye see very easily that you can write some algorithm that says, okay, here's my track, here's my cluster, combine them, give me my 3 momentum from the track, give me my energy from the cluster, there's my 4 momentum. And in practice, this is extremely, extremely complex, as there are many different situations that the algorithm needs to consider. If you think back about some of the event displays that I showed before, for example, the B quark jet in a heavy ion background, it would be very complicated to connect tracks to particular clusters because you have so many tracks and so many clusters, and you're limited potentially by your detector's resolution. So in practice, this is very complex. This is an example plot from an Atlas paper that describes their particle flow reconstruction algorithm that shows you some of the situations that the algorithm needs to consider. And they go into great gory detail describing these kinds of things in the paper. But for example, you might have one particle that corresponds to one cluster. You might have one particle that looks like it corresponds to 2 clusters. You might have many particles that look like they correspond to one cluster. You could have the opposite. So your algorithm needs to very carefully identify these things and try to appropriately assign tracks to the clusters that they really belong to. And again, in practice, particle flow algorithms are very, very complex, but the outcome of them is very nice and sort of what we want, because we want to identify 4 momenta of particle. We want to say, I had a pion, or I had an electron, or I had a proton, or whatever it is. And particle flow algorithms move us in that step by connecting the tracking information to the calorimeter information. So you can also use this for electron finding, for example, since electromagnetic showers are more contained than hadronic showers. You can make cuts on things like the energy of the cluster over the momentum. And you would expect that for electron showers, this would be very close to 1, because your electron should dump all of its energy into the EM cal. Whereas for hadrons, you should expect that it would be less than 1, because your hadron will dump only some of its energy into the EM cal. So you can match tracks to calorimeter clusters and make strong energy and momentum cuts to do some electron identification. These are two examples from EPIC and from SPhoenix, which show this, where this red is an electron distribution. Fortunately, they use the same colors so that it's not confusing. But the same thing here, and then over here, blue is pions, and then blue is pions over here. And you can see that the shapes of the distributions are extremely different. So this is one way that you can do some particle identification, for example, without actually having your PID detectors. Okay, so Luna talked a lot about jet finding already, but I just want to briefly mention it since jet finding is also a reconstruction algorithm. The physics definition of a jet is a spray of particles that results from a high energy parton. But again, I think it's important to keep in mind that the experimental definition is just what a jet reconstruction algorithm determines. So it is the output of a reconstruction algorithm. And you could give this jet finding algorithm a variety of things depending on what your particular interests are. You could give it calorimeter clusters, you could give it tracks, you could give it particle flow objects. A jet finding algorithm just takes something in and spits out what it thinks is a jet based on the algorithm's definition. So you, as the analyzer or the event reconstructor, could choose based on what your goals are to give it a certain type of object. So you saw this plot already, but this is just an example showing the different jet finding algorithms can associate different particles to different jets in sort of different ways, different shapes. Something that I think is cool that some recent work is some new jet finding algorithms that are maybe more relevant for an EIC. So the most common jet algorithm at Hadron Colliders, as we heard, is the anti-KT algorithm. But this is a nice plot from this paper that shows that with some new algorithms like what they call the Centauro algorithm or this spherically invariant anti-KT algorithm, you can actually more carefully separate out particles that are from the target and from the current, which refers to the sort of target parton in your DIS collision versus the remaining fragment that gets kicked out from your proton. And that may help you more cleanly identify sort of the partonic scattering in a DIS jet event. So this is ongoing research, and it's just I bring this up just to emphasize that event reconstruction is not just some solved problem that people did 20 years ago and it works for every experiment. Every experiment is different, and you need to tailor your event reconstruction to suit the geometry, the detector apparatus that you have, the accelerator conditions that you have. All of these things are important, and event reconstruction is a sort of active field of research as people try to find new and better ways to do these types of things. Okay, so let me make just a few comments about backgrounds and then I'll finish up. So event reconstruction is significantly simpler in the sort of single physics event simulation world where you just run some Pythia or something like this. But real life has contributions from many different background sources. And I think it's important to emphasize that at the EIC, this will be the case. And we have some studies now that sort of indicate to what degree this will be the case. So at an EIC, we will have backgrounds from synchrotron radiation, which is radiation from the electron beam that comes about from the electron being curved in the beam pipe. So it's radiating and it's accelerating. We will have backgrounds from electron and proton beam gas interactions. We will have beam pipe effects that may lead to backgrounds. And so our event reconstruction has to handle these contributions when we do our reconstruction. So just to give you some sense for the size of these backgrounds, these plots show the hit rate per second in various detectors in EPIC for electron and hadron beam gas. And these are expected to provide millions of additional hits per second in the detectors. So our event reconstruction has to be able to deal with this. It's not like, my simple cartoon before that has a single track going through our detector. We will have millions of additional hits from backgrounds in every single detector, or of order millions. And our data analysis, our data reduction, our event reconstruction pipelines need to be able to handle this to appropriately reconstruct the actual physics event that we want to analyze. And, say we learned something about the spin composition of the proton, or we learned something about the proton structure, whatever it is that you're interested in. So same thing for synchrotron radiation. This again just shows some estimates for the number of hits per second that will happen in each of our EPIC subsystems as a result of synchrotron radiation. So this is a really non-trivial thing. Okay, so some conclusions that I have to finish up. Modern particle physics experiments are an incredibly complex system of hardware, computing, engineering, and science. I think it's so important to emphasize this, and it's incredible. It's an incredible feat of humanity that we can build these things and operate them. It's truly remarkable. Things I didn't cover in the detail they deserve, which I think will be partly covered by some of the other lecturers, but not entirely. There's a big interplay between the data acquisition, streaming readouts, and reconstruction. You can imagine that event reconstruction is entirely dependent on what the data looks like coming off the detector. Event reconstruction in a triggered experiment where you have some trigger signal and you only read out the physics collision of interest, it is going to look very different than the event reconstruction at EPIC, where we have a continuous stream of data coming to us at all times. So there's a lot of interplay between data acquisition, streaming readout, and event reconstruction. I didn't talk at all about calibration. So we have to calibrate our calorimeter's energy scale in various ways so that we really know, I measured an 8 GeV electron and it's not a 4 GeV electron or something like this. There's a whole discussion that could be had about alignment of the tracking detectors. I told you that, tracking detectors have resolutions of order 100 microns or something. It is impossible if you were to take, suppose you were to take a silicon chip or something like that. I would bet $20 that you couldn't put it on the table and say, I know where that silicon chip is to within 10 microns. It's impossible to measure with that fine of resolution with a measuring tape or any sort of experimental apparatus. Now think about, you have a whole barrel of silicon, you put it in your detector, and you need to know where it's positioned with respect to all the other subsystems so that you can actually achieve the momentum resolution that is only limited by the intrinsic resolution of your detector. So tracking alignment is a complicated problem that is generally uses cosmic rays and tracks from your experiment to align the detectors to optimize and get the best momentum resolution out of your detector. There are all sorts of analysis techniques that come out after event reconstruction, like folding efficiencies, resolutions that you need to understand about your physics observables. There are lots of hardware and software R&D efforts that we could discuss, but there's lots of people who are pushing the field forward, and the EIC has certainly a long road ahead over the next decade or so. But it's very exciting as we're building a truly state-of-the-art machine at EPIC and the EIC. So I want to encourage you all to get involved. There's so much to do. I cannot emphasize that enough. So thanks for your attention. I'm happy to take any questions.
Thank you.
Do streaming readouts truly capture everything, or is there some threshold to prevent garbage from getting into your?
So detectors can have thresholds placed so that you can reduce the data rate. So for example, you could imagine kind of like what you're suggesting, that if you were streaming all data, your data rate might be something very large. But you could say, I only want to actually send to disk the data that looks a certain way that I expect it to. That will greatly reduce my data rate. So that's what you may hear the term occasionally, zero suppression. That is what the goal of zero suppression or thresholds are, is to suppress data that you aren't going to be interested in because it's not, there's no hit there or something like that. There was no signal. So you can suppress pedestal and not write it out to reduce your data rate. So that exists and is the case for most detectors nowadays to reduce data rates. But you have to also consider that you better be sure you know what you're throwing away, because if you don't, you've lost it. So oftentimes experiments will not zero suppress their or those thresholds to their subsystems until they truly understand what's coming out. And at that point, you could say, okay, I really know that, you know, if I get a channel that looks like this, that's garbage. So let's zero suppress it and not write it out.
So they'll start like zero suppressing like halfway through the experiment, something like that, like.
I don't know, halfway. I mean, it just depends on, it depends on the subsystem and how simple the readout is. Like, calorimeters are generally simpler detectors than tracking detectors nowadays. So they can usually move at faster speed because they're just easier to understand in general.
Well, the reconstruction algorithms have to change over time because all these detectors will get damaged from radiation, right?
That's a tough question. I mean, not necessarily. It depends on the level of damage, I would say. And that being said, I definitely will say that whatever the reconstruction algorithm is in Epic now will not be what it is in 10 years when the experiment turns on, because it will become more complex as we learn more about the experiment, we learn more about the accelerator. You know, there's more time, people have worked on it to make it more realistic, all these kinds of things. Reconstruction algorithms are constantly evolving and changing and improving. So I can give you my experience from SPhoenix that, for example, we rewrote the track reconstruction like 3 times over the past 8 years because of things that we learned on an iteration of having track reconstruction. We did it. We did a bunch of studies. We realized, hey, there's going to be a problem with this. Like, we won't be able to reconstruct our data because it's too slow, and we only have these many CPUs. So we need to change and do something else. So that kind of thing, I think, will happen, and it's important to make your reconstruction as modular as possible so that you can, you know, when you learn these things, you can swap something in and out, and it doesn't somehow break your entire software stack or something like that.
Let's thank you once again. We're on time, so let's come back here at 1 p.m.